Okay, so if you go to Blackboard and look at the announcements, you'll notice that there is a link in the announcements to the video recording from Monday night. That video recording, I'm going to start it up here. See, I don't know how much of this you'll be able to see, but that video recording, the beginning of it, I didn't get a chance to edit it very much because it's such a short time span. But you'll notice that it takes about 3 or 4 minutes in before we really get to work. And what we do in that video recording is we cover the idea, we very quickly talk about confidence intervals again, but then we go into hypothesis testing. And we talk specifically about doing t-tests, doing tests where we compare two means. In the case of this first section, which starts about 5 minutes in, goes on for about, we dragged it out, wow, goes on for about 20 minutes, 15 minutes or so. That part, it concerns single sample t-tests. And single sample occurs when we're dealing with a known mean for a population. We're sampling another population, and we want to know whether the mean for that population is equal to the known mean for the other population. Well, since we only know one of those populations by its sample, well, we're not all that sure about it. We use a t-test to determine whether or not those two means are equal. We'd set up a hypothesis test. I think you just saw briefly. Hypothesis, the steps in hypothesis testing: state the hypothesis, specify the significance level, the level of error that you're willing to accept, usually 5%, draw a sample, record the size of that sample, determine what, calculate a p-value or z-value, z-value if you know the population standard deviation, and a t-value if you don't know the population standard deviation. We're going to go over this in some detail again tonight. And then you determine the p-value, the probability that you would get that big a difference, that big a t-score. Remember, the z and the t-scores represent the number of standard errors difference between those two means. The probability you get that big a difference between the two of them in terms of standard deviations, or in the case of sample, standard errors. Okay, and if that t-score is big enough, if they're far enough apart, if they're, say, 2.5 standard deviation or a t-score of 2.5 apart, it's likely, in most cases, that we would be able to reject the null hypothesis and say that they're the same, and accept the alternative hypothesis that they're different. The p-value is a number which describes for that particular t-score and that particular sample size. It determines what the probability would be that we would be wrong in rejecting the null hypothesis. In other words, the probability that we get that big a difference in the two means, if the two means in fact were the same. Okay, we want that p-value to be less than our tolerance for error, which is our alpha, 5% one. So we want our t-value to be big. We want it to be bigger than what we call the critical value, and we want our p-value to be small, meaning less than 5% or less than the alpha that we wind up choosing if we choose a different one like 1% or something like that. And that's how we determine whether we reject the null hypothesis and say the two means are in fact different. Okay, so in the beginning we talk about a single sample t-test, where we're just comparing the mean against a single known number for the other population mean. Okay, then we go into two sample t-tests, and then we go further. We go into two sample t-tests where the standard deviation of the two groups is the same, and then two sample t-tests where the standard deviations of the samples are different. And we do it in a number of different ways. We do it using Excel, right? Here we are doing it in Excel, and then we repeated the same problem using SPSS. So what I'd like to do is, if you haven't seen this already, it's long. I want to give you about an hour to go through it, so you're not going to be able to, like watch the whole thing. But if you could scrub through it, kind of skip through the parts where, like, I go off on a tangent and stuff like that, and trust me, it's probably down to 30 minutes if you do that, right? So if you can at least go through at least the single sample t-test and at least one of the two tests for independent samples when we have two samples and we're comparing them to reject the null hypothesis. I'd like you guys to take a look at that. So I'm going to give you a little bit more of an introduction here, and then I'm going to send you off to watch that video. And this video, like I said, you can get to it by going to the announcements, and it's the second item down. It's this link right here. Okay. At some point, I'm going to put all these video links into the actual sessions themselves. Now, you may also, if you go into the sessions, okay, you can alternatively, tonight is July 9th, it's July 5th, session 9. You can alternatively, if you go in here, you'll see that I posted previous classes versions of this, except here I've broken it up into, this is a video which is, let's see how long it is, which is 15 minutes long, which is a single sample t-test. And this is a video which is 25 minutes long, which is a two sample t-test with equal variances. And this is another video which is 27 minutes long with unequal variance, a two sample t-test with unequal variances. So you can look at either one of those. I think the one that we did on, but did you tune into the one on one? Nope. Okay, the one we did on Monday night came out pretty good, so I wouldn't hesitate to maybe look at that one. And in fact, now that I look at this, it might be a few minutes, a bit shorter, especially when you skip through parts of it and stuff like that. So if you can, I'd like you to take a look at that. Now, again, I'm just going to quickly talk about how we got to this point. And then after we do that, I'm going to try a couple of examples where we can give this a try. Now, you're going to watch me do these problems using both Excel and SPSS. If it's possible, I may give you on an exam. We have an exam, by the way, coming up on Wednesday the 12th. I may give you a very simple example, like a single sample t-test, to work out numerically, like using Excel or a calculator or something like that. But for the most part, anything any more challenging than that, you're going to be able to use SPSS for. It's going to be much simpler and much easier to do. Okay, and also I might, in some cases, just print out tables and ask you to interpret the tables, which by then I think you're going to be pretty comfortable with. Okay, so here we go. Let's say we know that nurses usually watch their diet, and they have the mean cholesterol for all nurses in New York State is registered nurses. Let's say registered nurses, RNs in New York State, is mean cholesterol is 120. And we want to know whether doctors have a higher or lower mean cholesterol than nurses do. Well, the nurses union, is there a nurses union? Yeah, there is a nurses union, right? I know that PAs have a union. Is this the same as physician's assistants? Yeah. Yeah. So at any rate, the nurses union paid for screening, and we know that this is the true mean of all the nurses in New York State. Doctors, were obstinate. They have no union, and it was like hell to get them to agree to being tested. So we were forced to sample doctors in New York State, take a random sample of doctors in New York State, and we found that their mean cholesterol was equal to, and we're going to figure this out. I'm gonna talk about like it's a sample of 9 doctors. Their their cholesterol was 100, 150, 190, 140, 120, 110, 120. How many do I got here? Three. Want two more. 110, 110 again, and 130. Okay, so I add those all up. Somebody add them all up for me, and let me know. Actually, I'm gonna put them into Excel. Should have actually done that first. I'll do this. Gonna do this as quickly as I can. When we come back in the video, we do this with more time and care. So if it seems a little intimidating now, don't worry about it. It's gonna get simpler. Okay. Can you go back here and get that back? Okay, 100, 150, 190, 140, 120, 110, 120, 110 again, and 130. Okay, so I'm going to find the average for doctors. Average for doctors, mean, in other words, is going to be 130. So it's higher than nurses, but we don't know if that difference is due to chance or if we can say with some level of certainty that there's a real difference in the mean cholesterol for doctors and for nurses. Okay, so I'm gonna tinker with this a little bit. I'm gonna make this number 140. Make things a little bit more interesting. Okay, 133. Let's make this one a little higher too. 20. Okay, let's use that. So the mean is 134. Now I can calculate a standard deviation for this sample as well. And my presumption is, and my sample size, I'll mention my sample size is 9. So that's the mean, the standard deviation, and the sample size. Well, I know that by taking a sample from a population, random sample from a population, the mean of the sample approximates the mean of the population. The standard deviation of the sample approximates the standard deviation of the population. And the sample size, I know. Bigger the sample size is, the more confidence I have in the mean and the standard deviation. That just makes sense, right? We don't need a mathematical justification for that. We know that's going to happen. Okay, so now I want to say to myself, gee, okay, so now that I know that, how can I show that this mean, and at what level this mean is different from a population that has a mean of 110? I'm going to assume that they have the same standard deviation in the two populations for right now. Okay, so now, since I know that I'm working with a sample and not a population, I want to examine how repeated samples of size 9 would behave when I take the means of all of those samples and I look for a distribution. And we know that they're not going to be spread out the same way the population is. They're going to be spread out somewhat differently. They're going to be spread out by something called the standard deviation of the means, which is called the standard error. So that's going to be equal to the standard deviation of the population, sigma, if we knew it, divided by the square root of the sample size, right, which is 3. Okay, so my standard error is 8. Right, so let me just check to make sure there's no questions so far. Look at the chat box. Okay, good. We're okay. I think we're okay so far. So now, even before I started this process, one of the things I should have done, I should have stepped back and I said to myself, well, what is it I want to prove? What's my hypothesis here? Well, first of all, I start off always with a null hypothesis. Null hypothesis always assumes an equality. And then it's our job to prove that there's a difference. And in public health, that's usually what we're trying to do. We're trying to prove that a drug works better than a placebo, a intervention improves conditions, one ethnic group may have a higher incidence of some disease or may be impacted by something more than another. Investment in certain kinds of public health activities are going to improve or lower, say, homelessness. We're going to have some sort of intervention. We want to know whether it lowers or raises the rate of homelessness. So our assumption always starts off with an equality. In this case, the equality that we're looking at is the mean for nurses is equal to the mean for doctors, right? And our alternative hypothesis is that they're not equal. Okay, so that's really what I'm looking at here. I want to be able to reject this idea that they're equal and accept the alternative. But I'm only going to do that if my chances of being wrong, my alpha error, is equal to 0.05, 5% or less. Okay, we want less than 5% chance of being wrong if we reject our null hypothesis. That kind of ties into you guys recall our 95% confidence interval. it really ties into this idea of our 95% confidence interval as well. Okay, we're 95% certain that we can reject the null hypothesis. In other words, we think there's less than 5% chance that we would be wrong if we were to do that. Okay, so how do I know whether or not this mean 130 is far enough from this mean 110 in order for us to reject the null hypothesis? Well, the way we do that is we calculate a t or a z-score. Okay, that's the number of standard deviations apart that these two are. You know that number of standard deviations determines the probability that you would get that kind of outcome when we talk about standard deviations from the mean. So we're going to look at the standard deviation that these two means are apart. But, well, if we knew the standard deviation of the population, if we knew sigma, right? If we knew Greek letter sigma, we could then, we would be eliminating a large part of the uncertainty about doing this, right? And we would use the z table. We would use the z-score. And in order to be 95% certain in the z-score, we would be perfectly happy with a difference in number of standard deviations of 1.96. Same thing that we use when we use the 95% confidence interval. If we were two standard deviations apart, we'd be perfectly happy to reject the null hypothesis and accept the alternative hypothesis and be 95% sure that we're right, that they're really different, and have less than 5% chance of being wrong. Okay, now, problem is, since we don't know sigma, we're dependent on the standard deviation of this sample to give us an estimate of sigma. So in that case, we have to use the t-score. And the t-score is that we need to exceed in order to, in other words, a distance between these two means, that number depends on the sample size. The larger the sample size is, the smaller the t-value that we need to exceed, because we have more certainty. We don't have to have them so far apart. So that t-score is going to be dependent on what the sample size is going to be. We're going to take a look at a t-table momentarily. Let's see how we calculate t. So t is going to be equal to x bar minus mu. Okay, in the case where there's two means, we would put x bar 1 minus x bar 2. But in this case, we only have one sample and we're comparing it to a known mean. Okay, that's the difference between these two means divided by the standard error, standard error. Okay, so that'll give us the number of standard errors that they're apart. So in this case, it's going to be equal to 134 minus 110 divided by the standard error, which is 8. I got to put this in parentheses first in order to make this work. Okay, and that comes out to be 2.87, right? Well, if we knew the population standard deviation, sigma, and we got a z-score 2.87, we know that they're further apart than 1.96. We can be 95% certain that they really are different and reject the null hypothesis and accept the alternative hypothesis. But with t, we don't know that until we check how big a t we need for this particular sample size. So I'm going to go here, and I'm going to look this up. You should have access to this either in session 7 or session 8, session 8 and session 9, or in fact probably both. I probably put it in both. Okay, here's a t table. Oh, did I say that? Oh, okay, I lied. It's 110. Okay, I'm going to keep it 110 because if I make 120, if I make a 120, I'm not going to be able to reject the null hypothesis. So I'm cheating. Okay, I'm going to go back. I'll change that later on. So I'm going to cheat. Okay, so let's call it 110. I like that better. Okay, so the number we get is 2.87. So now let's check to see if our t-score is really that big, if our t-value is big enough for this case. Okay, so instead of talking about here's our critical values at t, now the thing with t is it's like a z distribution, right? Except for it depends on the sample size. The smaller the sample size is, the less certainty we have about the spread of the of these samples, right? So what happens is it winds up being a flatter distribution. Looks like normal distribution, has a lot of the same properties, but it's wider and flatter, right? So as the sample size gets smaller, it gets even wider and flatter, right? So we need to know what t values represent 2.5% in the top and 2.5% in the bottom. So we're looking at the middle 95%, just like our confidence interval. Okay, so we want that each tail to be 2.5%. So for each sample size, there's a different curve. So instead of giving you one of those tables like the Z table for every different sample size, so you'd have to have a book like an encyclopedia of tables. Instead, they only give you the t values that are important, the critical t values. Like for instance, one thing you should note is that instead of using sample size, they use degrees of freedom. Okay, and degrees of freedom is a sample size minus one. So the degrees of freedom in this case for a single sample is 8. So we're going to go from 8, we're going to go across, and you'll see there are different numbers that represent the critical values of t. For instance, this one in the middle, 2.306, that represents the critical value for t for a right-hand portion of the curve, outside the right-hand portion of the curve being 2.5%, meaning 2.5% in the top means 2.5% in the bottom. If you're the same number, if you're negative 2.3 t-scores, right? So that's basically 5% of the distribution is outside that. That's how extreme this would be if you got that t-score. That its corollary is a 95% confidence interval. So you can see 95% and two tails with each with 2.5%. That's the one that we're interested in this case. So I'm going to go down here. So the value of t that I want is 2.306. Now notice as the sample sizes get bigger, the t value that's represented by 95% confidence or a 5% chance of being wrong gets smaller and smaller and smaller. So the bigger the sample size is, the smaller the t value you need to exceed in order to reject the null hypothesis. We have a small sample, so we're going to be up here by 2.306. So what this means now is that if our t-score is bigger than 2.306, it means that we're more than 95% confident there's less than a 5% chance that we might have gotten this big a difference between the two means if the two population means had been equal, right? So this means that since this is bigger than 2.306, right, that means that we can reject the null hypothesis and accept the alternative hypothesis and still have less than a 5% error chance that we're going to be wrong. Now, when I do this with SPSS, not only will I see what the t-score is, but SPSS will give me a t-score of 2.306 means that you have exactly a 5% chance of being wrong if you reject the null hypothesis. If your t-score is bigger, the probability that you would reject your null hypothesis and be wrong is smaller than 5% because your t-score is bigger than you need it to be. So that might be I'm going to speculate 0.03, might be 3% chance of being wrong. SPSS will not only calculate for you the t value, but it'll also calculate that p value. It calls it significance, okay, or two-tailed significance. Sometimes you'll see it called, right? So that you have that benefit when you use SPSS in calculating this. I'll do that very, very quickly. I'm going to open up SPSS. Okay, and in fact, I think maybe if you, now that we've done this, you might be able to skip that first part of the video on the single sample t-test and watch it in more detail later, and just skip right to one of the two sample t-tests, where you actually take two samples, not comparing it to a known value. Okay, there's my numbers. I'm going to analyze. Now what I'm doing is I'm comparing means of two groups. In this case, I'm only working with a single sample and I'm comparing it to a known mean from another population. So I'm going to move that in there And the value I'm comparing it to is the mean for nurses, which I cheated and called 110. And I'm going to click on options. And in options, I can see, oh, well, the confidence interval that it's going to work with is 95%. So that is associated with 5% chance of being wrong. So I'm going to say, let's leave that just that way. I'm going to say, okay, the output window is going to open up, and hopefully we'll see some familiar numbers. And in fact, we see the mean that we calculated, right? That's the mean that we calculated from the sample. That's the standard deviation, and that's the standard error that we calculated manually. So SPSS then takes that 134, subtracts it from the 110, which is the mean of the population we're comparing it to, divides it by the standard error, and gives us a t-score of 2.87, just like we calculated just now. Okay, degrees of freedom are equal 8. And it tells me that the probability of being wrong, if we reject the null hypothesis, my p-value, my p-score, or my significance is 0.212% chance of being wrong. So since that's less than my acceptable level of error for rejecting the null hypothesis, 5%, I go ahead and I reject the null hypothesis and I accept the alternative hypothesis. Okay, so if you go to those videos now, I'll release you for a little while. You guys go to those videos, and let's say we come back here. It's almost 6 o'clock now. Let's say I give you about an hour or so. Let's come back here at 7:15. Right? Maybe a little earlier. Let's come back. Let's try and come back at about 7. That way we have some more time, because I want to start to introduce the next situation we might get into when we want to compare means. But I need you to view those so you get familiar with this idea of single sample and two sample t-tests. Okay, guys, so we'll bail out for now. Come back to the same link at 7 o'clock. We'll watch it in here. We'll play it in here as well. Okay, any questions so far? Yeah, go ahead.
So you said when you said the two-tailed, that p-value of 0.021.
Yep. That means
the probability of being wrong is 0.021.
Correct.
So
that's 1% in each tail.
So that's greater than
0.05. Right. As long as that p-value, that significance, is less than 5%, you can reject the null hypothesis.
Alternate hypothesis, which shows that the two means
of the populations are not equal. Exactly right. That's the whole point, is we're trying to prove that two population means are different. See, keep in mind, we never know the true population mean. We only know the sample means in almost all studies. So we want to understand how we want to find ways to quantify what our certainty is, how likely it is that we would be wrong if we say two means and two groups are different. Because that alpha error, there's two kinds of error, alpha error and beta error. Let's say, let's talk about this before you guys go away. Alpha and beta error. Okay, so let's take a look at this. Alpha and beta error, or type 1 and type 2. Okay, there are two different kinds of error. The alpha error, right, represents the probability that we would be wrong if we reject the null hypothesis. That's usually 0.05. Beta error is a whole other thing. We can calculate that. We don't focus on that so much when we're trying to decide whether to accept or reject the null hypothesis. The important thing is alpha error very frequently is more important to us than the beta error is, because that's our level of probability of being wrong if we reject the null hypothesis. And we're very concerned about that, because if we don't exceed that, let's say the p-value came out to be 0.07, 7%, we'd say to ourselves, we got very close, and the t-score was 2.1 or something like that. We got very close to rejecting the null hypothesis, but we didn't succeed. We failed to reject the null hypothesis. Now, we don't say we accept the null hypothesis. We say instead that we fail to reject the null hypothesis, because our real key here is we want to prove the alternative, that they're different. And why is it so important that we're right about that? Because if you succeed in rejecting the null hypothesis, let's say your p-value is 0.02, like this case, in that case, if you reject the null hypothesis, well, then you're going to say that, gee, that drug works, or that intervention works. We're going to spend a lot of money on that, or that diagnostic test works, or that association between this kind of food group and the outcome, or this treatment and the outcome. That works. So that means people are going to take action on that. So we're always worried about type 1 errors. That's why we're only willing to accept a 5% chance of being wrong. Even then, but you read plenty of studies where they feel they've proved to that level of certainty that say, I don't know, say saccharin causes cancer. But then somebody else goes back and tries to replicate that study and can't replicate it. And this kind of implies that up to 5% of the study results that you read could be incorrect, just because they got the differences because of chance, not because there's really a difference. Hopefully, it's less than 5%, because you're hoping that your p-value will be smaller than 5%, not always exactly 5%. Okay, so yeah, I was on Monday. On Monday, we're going to be talking about, tonight I'm going to introduce another concept called ANOVA, analysis of variance. Now, that's a mouthful, analysis of variance. Right, I'll spell it out here, variance. Okay, that's a mouthful. But believe it or not, you use analysis of variance to compare the means of different groups. Even though it's called analysis of variance, it's really a comparison of means. So an analysis of variance, you might say, let's say, for instance, we wanted to know the relative blood pressure, relative cholesterol of 4 different ethnicities instead of 2 different groups. So we would want to know, our null hypothesis might be the mean for group 1 is equal to the mean for group 2, is equal to the mean for group 3, is equal to the mean for group 4. We might want to know, gee, can I reject that null hypothesis and prove that the means for at least some of these groups are different? That's where we use analysis of variance. We use the t-test when we're comparing 2 groups, right? We use analysis of variance when we're comparing more than 2 groups. Now, you guys may have noticed that in the syllabus, I had t-test, and then I had chi-square and odds ratio. I'm moving chi-square and odds ratio to after the test and ANOVA before, because it makes more sense. We'll stick with numerical variables. We'll understand how to use these, because it's really doing the same thing as our t-test, but it's doing it for multiple groups at the same time. Okay, so it really kind of ties in better. In fact, dirty little secret, if you apply the analysis of variance to 2 groups instead of multiple groups, you'll get exactly the same outcome as you get for the t-test. Okay, but we won't discuss that. We don't want to talk about that. Okay, but that does turn out to be true. Okay, so yeah, and I'll probably do something over the weekend where we can do, maybe I'll post some sample questions or something like that, because we're getting into a little bit more elaborate kind of stuff, and I'll be posting a homework later on tonight for t-tests as well. Okie doke. Okay, so goodbye for now. Come back at 7 o'clock. What's that? No, we're going to go over analysis of variance on Monday, but I'll do something over the weekend. I'll post like a link. So over the weekend, like either Saturday morning or Sunday morning, whichever is the worst weather day, I'll do something on one of those 2 days where people can tune in. I'll record it, of course, so that you guys can, if you can't spare the time to tune in, that you get a chance to do that. And we'll go over some of these problems. I'll bring up some analysis of variance there too. But tonight we're going to introduce analysis of variance. T-test, the t-test, confidence interval t-test and analysis of variance will be the topic for the second exam. And I'll also by Monday, I'm going to be posting some information on projects. And I'm going to give you a choich at the end of the semester. You can either do a third exam to cover the last two topics, which are going to be chi-square and odds ratio and correlation regression, right? Those are the last two sessions. So you can choose to do that and take the third another exam, or you can. I'll give you some sample databases, and I'll give you some parameters that you can use, and you can choose to do a project by taking the data and analyzing the data on your own and putting it together, kind of in a report. Maybe it may be in the form of a poster if you guys have ever gone to poster sessions and stuff like that at conferences where people kind of like lay out their research on a poster. The third exam is going to be either, I'm going to make it flexible. If you, I know a lot of people have issues with the end of the semester. I've gotten a lot of emails about that. So I'm going to make it, I think it's the 24th and 26th. Is that the last 2 days? So the 24th and the 26th are dates that you're going to be able to. Now remember, one of those 2 dates you have to come in. Okay, either to do the exam. Okay, you can do it here either do the exam. I'll make up two versions of it or something like that, or to present your project. In other words, you do your poster or your research, and then you would take 5 minutes and present it to us. Okay, so not gonna be intimidating. When you see the layout on it and the parameters, it'll make sense to you. But I'm gonna make it flexible. So either of those 2 days that you can depend on. This coming Wednesday, July 12th, is required in class for the exam. But then that last exam or project, you have your choice of coming in the 24th or the 26th to take an exam or to present a project. Okay, but we'll get into that more. Okay, I'm killing time here when I want you to be watching that video. So watch the video for Monday night, and I would play it from here, except it does not. It's going to be kind of hinky. So it's better if you watch it, link to it on your own computers, and watch it. And I'm going to, for the two of us that are here, I'm going to play it in here so we can review it. But again, just we've gone through the single sample t-test and a little bit of confidence interval, so you can skip through that and maybe go on to the next and come back at 7. Okay, don't ditch me. Okay, I'm expecting you to come back. By the way, I noticed I'm trying to remember to make sure that I mute you guys when you join, but every once in a while people sneak in while I'm not looking, so I may not get a chance to mute them. But I can get some noise if your microphone is turned on in the background when you first log on. So just remember to mute your microphone when you log on later on. Bye. Talk to you later. Bye.